Welcome to the deep dive. Today, we're going to try something a little different and take a philosopher's perspective on something that you might not expect. Boolean algebra.
Boolean algebra.
Yeah. That math with trues and falses.
All right.
We've got the Stanford Encyclopedia of Philosophy's entry on it, and trust me, the connections run deeper than you'd think.
I can imagine. For a philosopher, this could get really interesting.
Absolutely.
It's fascinating how intertwined Boolean algebra is with, like, the core of philosophical thought.
Yeah.
I mean, you deal with two-valued logic all the time, right? Is a statement true or false? But Boolean algebra formalizes this and gives us a really powerful tool to analyze and manipulate these logical building blocks.
Okay, so let's get into the nuts and bolts.
Sure.
We're dealing with a set, operations like A and D, or, not T, and the special elements 0 and 1.
Right.
What's the philosophical significance here? I mean, for someone who's not a mathematician.
Think of it as a translation. Your set could be all possible propositions. 0 is false, 1 is true, and, or, not. These become the operators in your logical arguments.
I see.
The Stanford Encyclopedia uses the example of subsets.
Yeah.
Imagine ethics and metaphysics as subsets of philosophy.
Right.
The overlap, that's your aid-in operation.
Oh, so it's like a Venn diagram for ideas.
Exactly.
So we're visually representing how concepts relate to each other.
Yes.
And this isn't just some abstract game, right?
Yeah.
It's reflecting the way we, categorize and understand the world.
Exactly. And then there's the order relation, just like you have hierarchies of ideas.
Yeah.
Boolean algebra has less than or equal to. For example, human is less than or equal to animal because all humans are animals.
Right.
It's capturing the inherent structure of knowledge itself.
I see.
Yeah.
All right, so we've got the basics down.
Uh-huh.
But the encyclopedia really dives into the two-element Boolean algebra.
Yes.
Why is that so special?
It's the heart of the matter.
Okay.
This simple system with just 0 and 1 acts like a blueprint. Any equation that holds true in every single Boolean algebra must also hold true in this two-element one.
Oh, wow. So if we can translate a complex philosophical argument into a Boolean equation, and it works in this simple system, then it's logically sound no matter how complicated the original argument seemed.
Precisely.
That's amazing.
It's a really powerful tool for testing the validity of arguments and ensuring consistency in philosophical systems.
But there's more, right? The encyclopedia says that Boolean algebra goes beyond logic. It pops up in sets, rings, even shapes. How does that work?
This is where things get really interesting for a philosopher.
Okay.
Boolean algebra isn't just some isolated system. It's deeply connected to the structure of reality itself.
Wow.
Take sets, for example.
Yeah.
Remember those subsets of philosophy? That's Boolean algebra in action.
Uh-huh.
It's the math behind grouping and relating things in the real world.
So it's not just about abstract logic.
Right.
It's about how we organize and understand our experiences. That's pretty profound.
Absolutely. And it turns out this same structure is also found in things called rings.
Rings.
Yeah, they have different rules, but when you apply them in a certain way, you get a Boolean algebra in disguise.
So it's like this hidden code, this underlying pattern that keeps recurring in different areas of math.
Right.
But shapes, that seems like a huge leap.
It does.
Yeah.
But it speaks to the universality of Boolean algebra.
Okay.
There are these things called totally disconnected compact Hausdorff spaces, essentially specific kinds of shapes that have a Boolean structure built into them.
Okay, now my philosopher brain is really starting to buzz. What does it mean that logic, this tool we use to understand the world, is also woven into the fabric of math and even the shapes of space itself?
That's a great question.
Yeah.
And one that philosophers have been grappling with for centuries.
Right.
It suggests that Boolean algebra isn't just a human invention, but something more fundamental, a reflection of a deeper order in the universe.
Wow.
It's like a universal language spoken across different domains of knowledge.
Okay, I'm definitely hooked.
Good.
But before we get too lost in the existential implications, the encyclopedia mentions some key concepts: atoms, completeness, and free Boolean algebras.
Right.
What's the philosophical significance of these?
Think of atoms as the most basic units of truth in a system.
Okay.
In philosophy, these might be your fundamental axioms, the bedrock principles upon which your entire system of thought is built.
So it's about breaking down complex ideas into their most fundamental, indivisible truths, like reducing an argument to its bare essentials.
Exactly. Then we have completeness.
Completeness.
A Boolean algebra is complete when every single possible combination of elements has a defined meaning.
Okay.
Imagine a philosophical system where every statement, every proposition can be definitively classified as true or false.
Right.
That's the ideal of completeness.
So no ambiguity, no gray areas. Everything has its place within the system.
Exactly.
But that sounds pretty restrictive, doesn't it?
It can be, which is why we also have free Boolean algebra.
The Boolean algebras.
These are the wild west of Boolean systems.
Okay.
You're not bound by any preset rules or axioms.
Right.
It's a space of pure possibility where any combination of elements is allowed.
So it's like a philosophical playground, a space to explore any and all logical combinations, even those that might seem contradictory or paradoxical.
Precisely.
Wow.
And this raises interesting questions for philosophers.
Great.
What are the limits of logical systems? Can we ever achieve true completeness, or is there always room for ambiguity and uncertainty? Can we learn anything from exploring these free systems where logic is unbounded by convention?
This is really making me rethink the nature of logic itself.
It's fascinating stuff.
It is.
And things get even more fascinating when we start to consider infinity, something philosophers have always been drawn to.
Infinity, the ultimate philosophical playground.
Right.
But how does Boolean algebra, a system seemingly based on finite elements like true and false, even begin to grapple with something as vast and boundless as infinity?
It's a testament to the system's power and flexibility. We actually move beyond just lists of trues and falses. Those are still countable in a way.
Yeah.
Boolean algebra allows for structures that are truly infinite in nature.
Okay, you've piqued my curiosity.
Right.
So how do we explore this infinite realm of Boolean algebra? The encyclopedia mentions these cardinal functions are
Exactly. Think of cardinal functions like measuring sticks, but for infinite sets.
Okay.
They help us grasp different aspects of an infinite Boolean algebra, like comparing its size to other infinities.
Measuring sticks for infinity. That sounds like a paradox. Can you give me a concrete example of how these cardinal functions work?
Sure. Let's take the concept of cellularity.
Cellularity.
Imagine our infinite set is represented by a boundless library, each book symbolizing an element in the Boolean algebra.
Okay.
Cellularity asks, what's the largest collection of books, no two sharing any common themes that you can gather?
So it's like finding the most diverse collection possible, where each book represents a completely unique idea within that infinite library.
Precisely. It's a way of measuring how rich the diversity of the infinite Boolean algebra is.
I see.
Another fascinating cardinal function is independence.
Independence.
Here we're looking for the largest collection of books where none of their contents can be derived or explained solely by the others.
So it's like finding the most fundamental set of ideas, the axioms of our infinite library that can't be reduced to each other,
Sure.
but from which all other knowledge can be built. A bit like the fundamental principles in a philosophical system.
A very apt analogy.
Yeah.
And lastly, there's pi weight.
Pi weight.
This time, imagine trying to summarize the entire library with the smallest possible collection of books, ensuring you capture the essence of all possible combinations of knowledge within it.
So it's about finding the most concise yet complete representation of the infinite Boolean algebra, like distilling the core principles of an infinitely complex philosophical system.
You've got it. These cardinal functions give us a language to describe and compare different types of infinite Boolean algebras.
Okay.
And this has profound implications for philosophers.
Okay, I'm starting to see the connection. Does this mean that Boolean algebra can help us grapple with concepts like the potential infinity of ideas or the limits of human understanding?
It certainly opens up new avenues of thought.
Yeah.
If we can represent infinite sets within Boolean algebra, perhaps we can also model the infinite potential of human thought or explore the boundaries of what we can possibly know.
That's a tantalizing thought. But if Boolean algebra is so powerful that it can handle infinity, does that mean it can solve any logical problem? Can we always know the truth thanks to the magic of Boolean logic?
That's where we hit the philosophical bedrock of decidability.
Decidability.
It's the question of whether there's a foolproof method and algorithm to determine if any statement within a system is definitively true or false.
Decidability, the age-old quest for certainty.
Right.
So what does Boolean algebra have to say about this?
Well, thanks to the work of Alfred Tarski, we know that there is such an algorithm for Boolean algebra.
There is.
No matter how complex the equation, we can always crank through the steps and arrive at a definitive answer, true or false.
So Boolean algebra is like a perfect logic machine, always able to churn out the truth.
Yeah.
That's pretty impressive.
It is, but here's where the philosophical tension arises.
Okay.
We know that certain problems in philosophy, deep questions about the nature of reality, consciousness, free will, are considered undecidable.
So even with a tool as powerful as Boolean algebra, there are still limits to what we can know. Some truths might forever remain elusive regardless of how we structure our logic.
Exactly. It highlights the inherent mystery of the universe and the limitations of even our most sophisticated systems of thought.
This contrast is fascinating. On one hand, Boolean algebra offers this incredibly powerful tool for analyzing and manipulating logic, even on an infinite scale. But on the other hand, it bumps up against the inherent limits of knowledge and the existence of undecidable questions.
Yeah.
This really pushes us to think about the relationship between logic truth and the nature of reality itself.
Couldn't have put it better myself. And speaking of the nature of reality, there's another aspect of Boolean algebra that has profound philosophical implications. The ability to turn entire sets of sentences, like a philosophical theory, into a Boolean structure.
Wait, we can translate an entire philosophical theory into the language of Boolean algebra.
Yeah.
That sounds incredibly ambitious. How does that even work?
It's called the Lindenbaum-Tarski algebra, and it's a way of mapping out the logical structure of a theory, turning sentences into elements and their relationships into Boolean operations.
So it's like taking a complex philosophical argument and creating a sort of logical blueprint,
Yeah.
using the language of ANDs, ORs, and NOTs to show how the ideas connect.
Exactly. Imagine each key concept in the theory as a point on this map, and the Boolean operations A and D or R not as the lines that connect them.
All right.
The resulting structure reveals the underlying logic of the entire theory.
That's fascinating. So we're not just looking at the content of the arguments,
Right.
but the very way those arguments are structured and how they relate to each other.
Yeah.
Does this mean that different philosophical theories will have distinct Boolean signatures?
Absolutely. The Stanford Encyclopedia points out some remarkable examples.
Okay.
It turns out that undecidable theories, those where we can't definitively prove or disprove statements, have a Boolean structure that mirrors the rational numbers.
Wait, so the logic of a theory that grapples with unprovable truths reflects the structure of numbers that can be perfectly expressed as fractions. There's a connection there.
There is, and it gets even more intriguing, the theory of Boolean algebra itself when turned into a Lindenbaum. Algebra has the structure of pairs of natural numbers.
So Boolean algebra, when used to analyze itself, mirrors the structure of simple number pairs. It's like a self-reflecting mirror revealing its own inner workings through this mathematical mapping.
It's a beautiful example of how these seemingly abstract mathematical concepts can be used to illuminate the structure of thought itself.
Yeah.
And the implications for philosophy are immense.
I can imagine, by analyzing the Boolean structure of a theory, we could potentially gain insights into its consistency, its expressiveness, its relationship to other theories, and maybe even its connection to the nature of reality itself.
Precisely. It opens up a whole new dimension of philosophical analysis, one that goes beyond the surface level of arguments and dives into the very architecture of thought. But there's one final concept we need to explore, one that truly pushes the boundaries of what we consider truth.
Okay, I'm ready for the grand finale.
Yeah.
What is this mind-bending concept that's going to shatter my understanding of truth?
It's called Boolean valued models, and it challenges us to move beyond the binary world of true and false.
Okay.
What if instead of assigning just a single truth value to a statement, we assigned a value from an entire Boolean algebra?
So instead of saying an idea is simply true or false, we're saying it has a degree of truth, a kind of nuanced truth value that reflects its complexity. That sounds almost like fuzzy logic.
There are definitely similarities, but Boolean valued models remain grounded in the rigor of Boolean algebra. Imagine taking a complex philosophical argument and assigning a different truth value from your Boolean algebra to each component, each premise, each subargument, each conclusion.
So it's like creating a multidimensional truth landscape, where ideas are no longer just true or false, but exist on a spectrum of truth values that interact and combine according to the rules of Boolean algebra.
Exactly. It's a way of representing the inherent uncertainty and ambiguity present in many philosophical arguments.
Right.
And by analyzing how these truth values combine and interact, we can gain a much richer understanding of the argument as a whole.
This is incredibly powerful. But
Yeah.
where did this idea come from? Is it just a theoretical curiosity, or are there real-world applications?
What's fascinating is that Boolean valued models are closely linked to set theory, the very foundation of mathematics.
Oh, wow.
They allow us to explore alternative versions of set theory by changing the Boolean algebra we use to assign truth values.
So even the bedrock of math can be bent by Boolean logic. That's mind-blowing.
It highlights the incredible flexibility and depth of Boolean algebra, and for philosophers, it opens up a world of possibilities.
This has been an incredible journey. We started with the simple concepts of true and false, and ended up exploring infinity, the structure of theories, and even the very nature of truth itself.
And it all stems from Boolean algebra. It's a tool that empowers us to analyze, dissect, and ultimately expand our understanding of logic, thought, and even reality itself.
Well said. To our philosopher listeners out there, we hope this deep dive has shown you the power and beauty of Boolean algebra, a system that's far more than just a mathematical curiosity. It's a key to unlocking new insights into the world of ideas and the very fabric of knowledge itself. So as you continue your philosophical explorations, keep Boolean algebra in mind. It might just help you illuminate the hidden structures of thought and reveal truths you never thought possible.